So thank you, everybody, for coming to this presentation. I'm going to talk about crowd modeling and simulation, and I'm going to show recent results of a couple of projects related to crowd modeling. The first thing I want to present is our lab. It's called the Advanced Real-Time Simulation Lab. It's at Carleton University in Ottawa, the capital of Canada. And what we do is a bunch of different things. If you visit our website, you will see that this is only one of the things that we do. A wide variety of applications ranging from networking and telecommunications, methodologies, in particular parallel, distributed, and real-time simulation, and the application to robotic and embedded systems. And we are also focusing on how to use modeling and simulation to model different physical phenomena. The one that we are going to discuss today is crowd modeling. And everything that we do is based on discrete event systems. In particular, these are discrete event crowds. We're going to show what's the influence of existing biological models into these crowd models. And again, all that we do is based on discrete event system specifications. So what we do is based on a formal technique called DEVS, invented by Bernie Ziegler a long time ago, and it has evolved a long time. DEVS is a formalism. Everything that you do is, it has a mathematical background. You model your system using mathematical equations that are discrete event equations. And we invented a few years ago something called CellDEVS, which is a combination between something that looks like Cellular Automata and these DEVS models. The idea is that you have a grid of cells. Each one of the cells has a computing machine. This machine is implemented with DEVS. I don't have a good angle for the laser here anyways. So the idea is that when each one of the cells receive an input, it's going to activate. The cells are not doing anything, so you don't waste compute time computing things that are useless. And then when you receive an input, you activate a computation function that is going to maybe produce a state change. If nothing happens, the cell goes to sleep again, so you stop wasting compute cycles. But if something happens, you're going to inform a set of neighboring cells which will wake up and compute. You don't do that immediately. You do it after a delay. We have different delay functions, and this allows you to model delays of the behavior of each one of the cells in a very elegant way. We can formalize all of this. You can bring this to a board, discuss with your colleagues, and then we have a bunch of simulation tools that execute this using DEVS, abstract simulation algorithms, okay? So these abstract simulation algorithms have been proven to correctly simulate these models. We have this engine, everything works nicely, and we've been working on this for a long time. So I'm going to show you how we apply this technique. I'm going to show lots of application and videos and show the results of this. If you're interested in knowing about the technique, we can talk about it later, but I'm trying to focus on the application of the technique, okay? So you have a grid. On each cell of the grid, there is a computation engine that does this thing, receive an input, do a compute a function, get a new result, spread the result to your neighbors, okay? Now, we have we have enhanced the tools with a wide variety of visualization tools. We're also very interested in doing visualization of the results and including analytics of the results. So lately we have been combining these CellDEVS models with web-based simulation and distributed simulation and analytic tools. We have incorporated D3 and the R framework into our web-based version. And we have been using this for a while. So let me tell you a very brief project that we did using this. It was brief but interesting. So there is this company in Ottawa called Bental Kennedy. They manage buildings. They are the largest building management company in North America. They manage 40% of the buildings in whole North America. There is one building called the Sun Life Financial Center in downtown Ottawa. This is the building, okay? So there's a bunch of lawyers, there's a large number of offices, and what has happened recently is, so this is the main lobby of the building, this is the main entrance of the building, and what has happened recently is the following. Ottawa in the winter, that's the area that we're interested. They're building a light rail that goes from the east to the west and passes through downtown, okay? Normally, right now, there are buses, and the buses are far away from this building, okay? But there's a new rail station that's going to be very close to this entrance. So what's going to happen in the middle of the winter? It's warm, people are going to get into the building. So the Bental Kennedy was worried, well, not Bental Kennedy. The tenants of the building went to Bental Kennedy and said, this is going to be crowded, and the traffic, the through traffic is going to affect business here. In particular, if you see there's this corridor, people will enter through this door and will leave through that one. It's like 1 block long, and there are elevators everywhere. And so how is this going to affect when the light rail is there? So we conducted a study. This is the main corridor. And what we see over here is a CellDEVS model. It's a 3D visualization of that CellDEVS model. This is how the corridor looks like. So these are the floor plans. So what we did is web-based implementation of the CellDEVS model using human behavior. People get into the elevators, and we were able to prove that even with the worst possible amount of people at the peak hour in the light rail, it's not going to affect the corridors. The tenants wanted Bental Kennedy to build an alternate path for people, and that wasn't necessary because of the result of this study. So these are the kind of things that we do. And we've been doing pedestrian modeling at this scale for a while. What are the advantages of using DEVS and CellDEVS? Well, the idea of DEVS is that you can have many small models coupled together to represent a complex system. So in this case, we have models of the elevators. We have DEVS models of each one of the elevators. And each one of them is a discrete event model, and connecting the elevators model with the pedestrian model here is seamless. Connecting the input and output flow of the pedestrians is trivial. We have a light rail model that we have all of the stations, and we can say, okay, it's a fluid-based model. People will leave the train at that station, and they will enter the system. We can connect this without any problem. So we can connect a cellular model with a traditional sequential control algorithm for elevators with a large-scale rail model, and this works out really, really well. Okay, we can model the sliding doors, revolving doors, escalators. So the integration of these models is seamless. But once we solved this issue, we said this is what we want to do. Okay, so Ottawa in the winter, it's not a big deal. This is the Guangzhou train station every day. Okay, so how do you model something like this? It's not easy, okay? So there has been people that have been modeling this stuff forever. Now, to put what I'm going to show into context, there are 3 things. So we have considered separation of concerns into 3 levels, and we have talked with psychologists and biologists. When we plan paths, this maps very nicely what happens in the human brain. There's a cognitive model that says, I want to go home, okay? And then there is a global pathing that says, how do I go home? So home in this case is my room. So what do I want to do? Do I want to go for coffee, the coffee break, or do I want to go to my room? So this is resolved over here. We don't do that in this presentation. The second thing is, okay, I have now decided coffee break. How do I get there? So there is a path to go there. There are many ways. Do I take the elevator? Do I take the stairs? Do I go to the left? Do I go to the right? Do I go to this corner, to the other corner? I want to go to the tasty pastries. They are in both tables. Which one do I choose? This is resolved here. I'm not talking about that here. I'm talking about the local dynamics. Coffee break, everybody, so coffee break. So how do I deal with the local interactions when we all go to the coffee break? So this research is about that, and how do we deal with the local dynamics? It's a dense modeling technique, and the density is 10 square feet per person. It's a tiny, crowded place, okay? There are lots of models that exist for doing local dynamics. So a brief summary of the ones that have been used recently. Macroscopic view, it's like fluid dynamics. There's a velocity space optimization that use vectors, and there's the most popular ones are the force-based models right now that they consider the bodies as they have mass and forces and physics, etc. Okay? We don't like any of this. Why? Because these things happen. They cannot model properly pedestrian behavior in large crowds, and this has been observed in many simulations. There's herding behavior, and this does not happen in real life. There are two doors. The simulation will put everybody herding into a given door, even though there's another one very close. And it's a very hard problem to solve, okay, in terms of the algorithms to do it. So there are patches for everything. One of the patches are based on something called the local avoidance model that's based on psychology. And if you see how this is resolved, it's extremely complicated. Doing pedestrian modeling of hundreds of thousands of pedestrians using this kind of avoidance model is extremely hard. It uses a very complicated psychological model that we don't like, okay? But working with colleagues in biology, we found out something that's extremely cool, which is the following. It was cool because we had the solution to the problem, and we found out that biology matches our model, okay? So while trying to do validation of this, our physiology matches what I'm going to show. The hypothalamus in our brain makes us avoid people and behave in crowds in exactly the same way that our model does. And how is that way? Basically, we take care of personal space, and if there is space, we move around. So I can move wherever I want, I don't care about anything. There's plenty of space around me, okay? But if things get bad, your personal space compress, and you're okay with this. You're in a concert, you're looking at your favorite star, and you're jumping in the middle of the crowd, and you don't matter. Your personal space has been compressed. Your hypothalamus says, this is good, you're having fun, okay? And now, if you need to avoid people because, I don't know, you're feeling sick or you want a beer, you're going to move around this area, and so your brain tells you how to do this, and mostly what you do, and if you think about this, the next time you are in a crowd, you do this naturally. You avoid people. There's a bunch of people over there, there's space over there, you take a detour, you avoid people around, you go around them, and you get there faster. It's not because it's faster, because you don't want people to touch you. They're invading your personal space. Going in a straight line and pushing people, it's faster. So if I'm late for a plane because my flight was delayed because of the same snowstorm, and I'm running, I'm not going to go around because of my personal space. I allow it to be compressed, and I take the shortest path because it's less running. So this is what the model does. We try to avoid the violation of personal space. So this is a human, and this is the personal space. First question is, well, but the personal space is different in every country. Yes, we know. This is a single parameter in the whole model that you can change in 2 nanoseconds, okay? And so if you have people in a room that there's a third from New York City, and a third from upstate New York, and a third from Albany. So New York City, people have a smaller personal space because it's crowded. The farm, people have more space. Albany, it's a smaller city. There's something in between. Every person can have their own personal space different from the other, okay? Normally, when you see crowd modeling, the radius considered for a person is 0.8 meters. Okay, this is the standard metric that's used, and we use that as default, but we can change it. So this is the person, and this is the personal space of the person. What do we do? There's another person coming. As you can see, the personal spaces are going to collide. The people are not going to collide with each other, but when this guy moves, the two personal spaces collide. So what do? We move the center, and we create something which is called a centroidal, and we move the center from the center. You know, so the center of the circle is displaced in the direction of the forces provided by the personal space. And then we move people around. So it will go like this. Somebody's coming, personal space collide, they move, and they separate, and they continue their path. So we call the mechanism the centroidal particle dynamic method, okay? We combine this with the direction vectors, and then we have a combination of everything, and people move around, okay? Good. What will happen is that when you have a lot of people, a crowd with thousands of people, all of the personal spaces collide. So we find the intersection, and we find how they get compressed to each other, and people will try to move in every possible direction. There's space around it, so they can move, but if there's more people, they won't, okay? Now, the interesting thing about the method is that we create a personal space map, and we can map a crowd in this personal space map. So you have these people walking around, they go in direction of the exit. We create the personal space map, and this is how it looks like. And it's very simple. It's a bunch of cones, okay, that intersect each other. Doing the equations for the intersection of the cones is simple math. It's a basic trigonometry. It's done very easily, but the good thing about the method is that you can compute the personal space of each one of them individually. What's the good thing about it is that you can put each one of them to run in a different processor, and we have done that. So this runs in your GPU. We thread each one of them, and it runs extremely fast and with lots of efficiency, okay? So let's start with the examples. This is a very simple scenario in which we diffuse an overcrowded space. In this case, there's no global navigation, there's no destination, and this iterates until the level of energy gets minimized. So let's try to start it again. Oh, let me see. So as you see, it started as a donut, and it started diffusing following what I just told you. People try to move around to avoid collision with the personal space, and when energy is at the minimum, the simulation stops. Why is this useful? Well, you can use it for scenarios like this. You can use it for diffusing overcrowded space. Imagine that you go to a concert or to a religious event, and the doors are locked, and then they open them. So there's a crowded area over here, there's a lot of space here. What's going to happen? People are going to go quickly to the area that has more space, like in the video, okay? We use this for validation of the method, right? We have lots of videos, everything's been validated. Everything that I show is validated. The interesting thing is that none of the behavior that I'm going to show is programmed. It's all emergent behavior. We get the behavior of what I just told you, and it works beautifully. As you can see, the personal space has expanded, and the simulated version does exactly the same, okay? So you go from crowded area, the personal space starts expanding. When there's personal space, so there's space to move around. You use it completely, but as soon as it gets crowded, your personal space gets compressed. And so we have done validation of the model with those videos, and they match perfectly. Next. Good. Start of a marathon. People spend a lot of time doing these stop-and-go waves, programming them. Nothing to do. You say, we're going that way. you try to gain personal space. If you're faster than others, you're going to avoid them, and you're going to crash your personal space. And again, this is the video that we have used for validation, and so the acceleration delays that are also complicated to program, they're all embedded in the method. We don't do anything for that. Next, things like a crossing in this area. How do you do crowd dispersal or crowd gathering? In this case, it's gathering. In this case, it's dispersal. So people are crossing the road in different directions. Each group needs to go to a different area, and it works seamlessly. Basically, we say each one of them have a destination and go, and they avoid each other like they do in the middle of the street. We don't program this avoidance behavior. They move around, and again, we validated this. The most interesting scenario related to crowd dispersal and gathering is this one. People spent a lot of time doing bidirectional flow modeling. It takes a lot of time. There are lots of research about this. People try to mimic what we see over here. When you have bidirectional flow, there are lanes that are naturally formed. There's no one that says, follow me and go. They are formed naturally. And people try to do this in simulations. And as you can see over here, we get formation of these lanes automatically without us programming that. We have done validation of this. This is video footage that we got from a study that's publicly available. Everybody has, people have sensors, so there's data points available from this study, and the videos are available too. We have used the data points to check the proposed CPD method, and it works beautifully, okay? Now, I'm telling you this works very nice, etc., and you don't trust me. Let me show you the top research in the world in this area, okay? So people use this for animations and well, not only for crowd behavior, but animation and games, and they want to mimic the human behavior properly. So there was a paper in SIGGRAPH Asia 2 years ago. Group A, Group B, they want to do this. They want to do bidirectional flow and lane formation, okay? Model A, Model B, Model C, and Model D, okay? This is us, and this is SIGGRAPH. (600 entities, we have models with over 140,000 entities doing exactly the same thing, okay? So look at that, okay? This is the top graphical research in this field. Well, there's one from last year, even newer, come on. Okay, there you go. This is the best that's available. This is the state of the art in graphics, okay? And this is what the method does for that very complex problem. This model over here, as I told you, we have models with 100,000 of entities. This one has around 4,000 entities. Now, in terms of validation, so these are the data points that we obtained from that database that I mentioned. This is a trace of our virtual pedestrians, and if you take a slice of all of that, we have been proving that we have very good approximation of the results with a very little margin of error. Now, what's the interesting part of this? It's all emergent behavior. The only thing that we do is, I am here, this is my personal space. I see you coming, our personal spaces collide, I'm going to move a bit. Okay, I'm going to move my centroidal, and I'm going to put thousands of people to do this and see what happens. Well, it works also for other things. People have tried to model this behavior also, and it's doing complicated equations. We don't need to. Okay, this is called a petal formation. So there's a point of attention, and somehow, if you take a look at the crowd, there are petals formed because people are trying to look at the center of attention. Okay, this is naturally formed, and people try to mimic this. in our case, it's done automatically. So these are the heads of a crowd using the method. The point of attention, is here. And I will show you in a second. So the petals are from, there's an exit here, okay? And this is an actual scenario in which they tested evacuation of the area. Petals are formed at the exit. And if you see how people model this kind of evacuation, the algorithms are fairly complicated. We use CPD for the same thing. So our proposed CPD works beautifully without many complications. And this is, again, state-of-the-art in SIGGRAPH. The behavior observed has nothing to do with reality, okay? Now, a very nice side effect that we didn't plan, we don't care about performance. We want to come up with a new method, but the new method is also extremely effective because we can put each of the persons in a different thread. So let me explain you this graph. Frames per second, okay? This is how we measure performance. Why are we interested in this? Because we want to do visualizations that look realistic. And if you have very low frames per second, you will see the crowd moving every 10 seconds, and it's not realistic. You want the visualization to look fluid. You need at least 16 frames per second for that to happen. So for small crowds, in a desktop with a dedicated GPU, we have been running at 256 frames per second, which is extremely high definition for very small crowds, but we've been running over 100,000 in those at decent performance compared to others. If you see, we can run around 10,000 at decent visualization performance. And my student has been putting his stuff in his cell phone also. It's a good cell phone anyways, with a good GPU. But he's been, so I have a demo in my cell phone, which is not that good, but it works, with 4,000, 5,000, 6,000 people walking around at decent performance for visualization. Okay? Good. How?
You have 20 more minutes.
Ooh, I'm going very fast. I'm almost done. Anyways, so where are we going from now? So there has been a very well-known disaster in Germany in 2010 in the Love Parade. The issues that there were 2 entrances to a given avenue that didn't have exits. You see, it's cement walls, and when people started to push, it was a disaster, okay? So we could use the method for contingency planning in cases like this and have a large crowd like this properly modeled and simulated. Something else that we are planning to do is to do a full analysis of GPU acceleration, and we didn't even spend much time in performance of the model, and it works nicely without doing much. So if we spend some time in, focusing on how to make it faster, probably we're going to gain a lot. Right now, we have done standalone analysis of the videos that I showed you. What we want to do in the near future is integrate it with global pathing, so to get to the next level. We're working on density estimators, metrics, and we're working on high fidelity visualization. So I don't know if you saw this, but so each one of these dots correspond to, this is a trace of the dots, oh, come on, correspond to each one of these. And if you pay attention, I don't have a zoom in this one, there is an avatar on each one of them. It's not only circles colliding with each other. There's a tiny little person on each one of them. The issue is that these people are not moving, they're fixed, okay? It's a complete human, but it's fixed. So what we want to do is we want to put clothes, and we want to put different clothes, and gender, and height, and different weight. And these take more compute cycles, and we have started doing that. The first version that we have are these cool astronauts with the white spacesuits, okay? We want to do higher fidelity visualization. Something that we have already started to do moving forward. So there's a meetup over here. So you see the two yellow dots. So there's a crowd of people moving, and they're calling, "Mommy, mommy." So how do we integrate meetup behavior in the middle of a crowd? Again, this is something that has not been explored yet, and we have done the first experiments. This has not been validated yet. We don't have data for validating meetups. So we are going to do validation about this in the near future. And a second thing that we're exploring is intentional congestion. So there's a group of people here that are not going to move, and they're going to create congestion in the area. We have been doing comparisons between a model with the intentional congestion and the same one without congestion. And there are, so you know when there is a traffic accident, or traffic congestion, the effect goes backwards in all different directions that you don't expect, okay? The same thing happens here. You will find in this area over there, and in this area over there, and in this area over there around, far away from the area of congestion, congestion that does not exist when these guys are not there. So we are trying to study why this happens and trying to find models to, visualizations to validate. This is pretty useful for scenarios like this, like when you have people with, in a bridge, like in this case. Let me show you a video, okay? Good. So you have a bridge here, and people are selling stuff, and we want to try to reproduce this behavior. The guys don't move, and so behavior without the guys selling stuff, behavior with the guys blocking the path. We have some information about these models, and we're going to validate them, okay? Good. So a final thought is, some people say, okay, this personal space is not compressible. Is personal space compressible? So let me tell you that I believe it is. It's crowded, eh? Not anymore. You know what that is, right? You see the bull? It's San Fermin in Spain. The people. So, did you see how we move from case? Oh, sorry. Case A to case B. Oh, there you go. One more. It looked crowded, and suddenly it's not crowded anymore. Look at the space being compressed. Some people are happy. Good. I think I'm done. Anyways, we have more time for questions. Oh, okay. So, what's going on? It stopped. Yes, I know. I have it here, but not there. Let me try to start it again. Maybe it will. There you go. There you go. Good. So I want to thank the 3 students that participated in the project, that they did this nice logo for the lab. Omar is the expert on this version of the crowd models. Michael worked in the Bental Kennedy project, and he came up with the first versions of the algorithm. Ala did an extended version of Michael's model before we got into this. If you need more information, this is our Twitter feed. You can check our website later. And that's it for today. Thank you very much.